Okay, so in the last video we were talking about path connected sets and simply connected sets and the difference between them and conservative vector fields. And we finally got an idea of what a conservative vector field is. It is, by definition, the gradient of some three-dimensional function. The problem is, I could start with a three-dimensional function and then find its gradient, and then use that to create my vector field. But generally speaking, that's not how it works. We start with a vector field, and then we say, is it conservative? And how exactly do I go about determining if it is the gradient of some function? And there's a theorem that we're going to use here that'll give us a test for determining if something is conservative. And then we'll go from there and look at algebraically solving problems with it and kind of seeing where that takes us. And on the plus side, we're really only going to go over one thing here, one theorem and what it means. But the algebra involved is going to be extensive, which is what I was kind of leading to last week when I cut the lecture in half, because this is going to take a little bit to kind of work out. But as far as a test for a conservative vector field, so we have to have all of our conditions. Let f of x, y, z equal pi plus qj plus rk, where p, q, and r are my three variable component functions that we know. So let that be a vector field on an open, simply connected domain F contained in R3. First part of the condition's done. Whose component functions P, Q, and R have continuous first partial derivatives then F is conservative if and only if the following are satisfied. So we'll just write it this way. The partial of p with respect to y is equal to the partial of q with respect to x. The partial of p with respect to z is equal to the partial of r with respect to x. And the partial of q with respect to z is equal to the partial of r with respect to y. So if I have a vector field with component functions p, q, and r, if these three conditions, these three equations happen to be true, then I have a conservative vector field. And a couple of things. One, where these come from is essentially unknown at this point. We need more math to get to it. We'll actually get to it in chapter 7 and see where these functions, where these equations derive from. And again, I would also point out kind of the ultimate goal here. What this is telling us is, if I give you a vector field, you can now show, if these equations hold true, that the vector field is conservative. It does not actually tell me what my function f is that would have this as its gradient vector field, conservative vector field. It just tells me that that function f actually exists. And if you all kind of see the writing on the wall here, that means what we're going to have to do, and by we, I mean you, is if I give you a vector field, first test if it's conservative, then once you can show that it is conservative, then figure out how in the world to actually figure out what that potential function is, that function f. And, well, that's where all the algebra is really going to come in. The other thing, we want to actually prove this. We all know how an if and only if works. I have to go left to right and right to left. As it turns out, the backwards form of this, going from if this is true, F is conservative if and only if the following are satisfied. If these are satisfied, then F is conservative, the backwards direction. We can't actually prove that now. We need a theorem that we're going to see in chapter 7 called Stokes' theorem. So we're going to prove this, but we're actually only going to prove the forward direction. If F is conservative, then those have to be true. But since I only have this whiteboard, and this is a video, so I'm sure you're all taking notes and writing it down, I have to erase all that to give us room. So our proof, going in this direction. Suppose that F is conservative. That means that there exists some function F such that the vector field F is the gradient of F. But now, since this is true, I'm just going to plug in my potential functions here, my definition of F, and my gradient here, because this then implies that the function F, which is P I plus Q J plus R K, is equal to the gradient of F, which by definition is the partial of F with respect to X, I, plus the partial of F with respect to Y, J, plus the partial of F with respect to Z, K. And one other thing I'll point out, I'm just writing these as P, Q, and R because we're going to use them so often. And we've established writing the same thing over and over really gets redundant here. We understand these are functions, P of X, Y, Z, Q of X, Y, Z, R of X, Y, Z. That just makes this really cumbersome writing that out every time. So essentially I'm just going to call them P, Q, and R, and we understand that they're 3 variable functions. But now, if these things are equal, which again, by supposition they have to be, then these have to be equal term by term, which then means that P is equal to df dx, Q is equal to df dy, and R is equal to df dz. But now, in the conditions for this theorem, this test, we said that my vector field F had component functions P, Q, and R, and that those component functions had continuous first partial derivatives. Which means, since this function F, lowercase f, has continuous first partials, right here, and I know that the first partials of P, Q, and R exist, it actually means that this F has continuous second partials, because I know I can take the partials here, which means I can take the partials here, and they have to be equal. So, now take those partials, and let's see. Here, I'm going to take the partial dp dy with respect to y. So the partial of p with respect to y, which will then give me the partial with respect to y of df dx. And I'm only going to focus on this one and leave these off for now. So now I get that, which is equal to the second partial of f, partial y, partial x. But then we know, since I have these continuous second partials, the order of taking the partials can be flipped. So this is dy dx, partial with respect to x. I can actually flip that and write it as dx dy. But then this is just the partial with respect to x of df dy. But then right here now, I know the partial of f with respect to y is q, which then means this is the partial of q with respect to x. So now the partial of p with respect to y is equal to the partial of q with respect to x. And, assuming you took notes on it, that was the first equation that we needed to be true for this to be for this to be conservative. Now I could do the exact same thing here for this one and here for this one, just taking different partials with respect to x or z based on which one I'm doing. Do this same algebraic trick, flip the order of partial differentiation, and then just rewrite it in whatever form I needed. So I'm not going to take the time to write those out. You, in your spare time, should. Again, it's an identical proof, just with different letters in there based on which one I'm doing. So walk through them and make sure you can actually get them to work. And then, like I said, that will prove the left that if it's conservative, each of these equations hold. The backwards version, we can't actually prove yet. So we're going to save that for chapter 7 when we get to, again, what's called Stokes' theorem. One of the fundamental theorems to this entire class. But what that means is, now, if I have a vector field, I can see if it's conservative or not using those 3 equations. So as an example, prove that f equal to yzi plus xz, that's a terrible z, j, plus xyk is a conservative vector field. And again, we have those 3 conditions, which now we have a little bit more room, so I'll write out right over here. We need partial of p with respect to y to equal the partial of q with respect to x, the partial of p with respect to z to equal the partial of r with respect to x, and the partial of q with respect to z to equal the partial of r with respect to y. So basically, given that vector field, find all of these and make sure I get what I want. So, first, partial of p with respect to y. P, we remember, this is p, this is q, and this is r. Partial of p with respect to y is z. And partial of q with respect to x is z. Z equals z. So those are good. Then I need the partial of p with respect to z. That's y. And the partial of r with respect to x is y. Y equals y. Second test is good. And third, I need the partial of q with respect to z. Q with respect to z is x. And the partial of r with respect to y. R with respect to y is x. X equals x. That works. All 3 equations are satisfied, which means that is a conservative vector field. And again, this one is pretty straightforward and simple. The procedure is the same regardless of the vector field I have. Take all the partials, and then just see if I get the equalities that I need. If I do, it's conservative. If I don't, then it's not. So now, well again, that means now I know what a vector field is. I know so far what the curl of a vector field is. I have equations to find the curl. I know by definition what a conservative vector field is. There's a function that in the vector field is the gradient of that function. Now I have a test to, given a vector field, determine if that vector field is conservative. Hey, this one is. But again, we understand how this works. Now I say, hey, if that is a conservative vector field, then what that means is that f is equal to the gradient of some function f. And if I know this, the question is, can I find that? Can I find the f that will have this as its gradient? And the algebra for that is going to be a little bit involved. And the way we're going to go about doing this, we do this in other areas in math too, where essentially to kind of figure out the trick, we're actually going to start with a function f, find its gradient, then let that gradient be my vector field f, and then I'll say, since I know what this vector field f is, and I know what it should turn out to be, how can I go about algebraically generating that and get back to where we started? Similar to foiling and factoring, you start going forwards, then you use your understanding of going forwards to go backwards. Same principle here. So, let's see. And I will stress again, this takes a lot of algebra. I'm going to try to do this all on this board without erasing anything, but I make no guarantees. So we're going to let f equal xyz plus x squared y plus xz plus yz plus x plus 2y plus 3z plus c for any constant c. Now, and I'm deliberately going to try to color code this, I need the gradient of f. Gradient of f, partials with respect to x, so that's yz plus 2xy plus z, no x, that's a 1. No x, that's a constant, so there's the x. Then the partial with respect to y, which will be xz plus x squared, partial with respect to y, no y, plus a z, no y, plus a 2, constant again. Then partial with respect to z, which will give me xy, that'll be 0, that'll be x, that'll be y, that'll be 0, that'll be 0, this will be 3, that will be 0, and that should be my gradient, and it appears to agree with my notes. So now, this will then become my f. And the question is again, given this f right here, this vector field, which I could show is conservative using those 3 equations that we had before, can I somehow start with this, knowing it's conservative, and algebraically find that f up there? Well, let's see. I define f as pi plus qj plus rk, my standard setup. And now we've got all the setup that we need. But then I know by definition, whatever f is, this p right here has to be the partial of f with respect to x has to give me p. The partial of f with respect to y has to give me q, and the partial of f with respect to r, with respect to z, has to give me r. And then all of you say, hey, that kind of looks like stuff we did in Calc 2 when we solved differential equations, or if you've already taken differential equations, those are a bunch of differential equations. Admittedly, they are not actually differential equations. They're technically partial differential equations, because these are partial derivatives. Why did I make that one not a partial? Make my Kirby D. There we go. Which means I just have a set of partial differential equations, and I just need to solve the system of partial differential equations out. As far as solving it compared to a regular system of differential equations, the method is incredibly similar with one notable exception, which we'll see as we go through this. But essentially, solve these. And then somehow derive that right there. So, because let's face it, if I can solve these, I'll get f out, which was my goal. And I just have to pull f out of all 3 of those simultaneously. So let's see. I know right here, since I already found my gradient and this is my f, I know that p is equal to yz plus 2xy plus z plus 1. Which then, of course, implies that since p is also the partial of f with respect to x, the partial of f with respect to x is yz plus 2xy plus z plus 1. Now, change my colors again. To solve this easily enough, I'm just going to integrate with respect to x. On the left, integral derivative cancels out. I'm just left with x, f. On the right, integrate with respect to x, and I get xyz plus x squared y plus xz plus x. And now here, again, technically I'm integrating, but I'm actually partial integrating, if you will, because this is a partial differential equation. The only difference between solving a regular differential equation and a partial differential equation for the purposes of this, I do not get a constant at the end. Because I know that I integrated partially with respect to x, I knew this was a partial derivative, which means there could be other terms involving y and z that are not constant. This implies that it's a constant. There could be y and z terms floating around in here that I also lost when I took my partial with respect to x. Which means, instead of getting a constant, I just get a function in terms of y and z. The whole thing could turn out to be constant, we don't know. I just have to allow for the possibility that there could be y and z factors in terms in there. But now I solve for x. I've solved for f. So what next? Well, now I have f, and I will point out again, because we knew where we started, xyz, x squared y, xz. So this is clearly working, but to actually get the explicit form of f, I need to solve out for this function right here. And how am I going to do it? Well, I'm going to use the other two equations that I haven't used yet and build step by step. So then let's see. I know that df dy is equal to q, which is equal to xz plus x squared plus z plus 2. But now I have f, so if I just take the partial of f with respect to y and set it equal to this, see what I get. So the partial of f with respect to y is equal to xz plus x squared. With respect to y, that's 0, that's 0. I don't know what this is, but I know there could be a y in there. So I guess the best I can say is the partial with respect to y of k sub 1 yz. Because I have no idea what this is, so I have no idea what the partial will actually look like. But this has to equal xz plus x squared plus z plus 2. But then, since they're equal, the xz's cancel, the x squareds cancel, and now I'm left with the partial with respect to y of k sub 1 yz is equal to z plus 2. Ultimately, I need to find this function so I can substitute it in. So how do I get rid of the partial with respect to y? I do the same trick I did there. I integrate with respect to y. Now, those cancel out, and I get k sub 1 of yz is equal to, with respect to y, that's zy plus 2y, plus, here again, I don't get a constant, I get some function of z. But now, well, I know what this is, so I can actually go over here and replace k sub 1 with the k sub 1 I just found, which is zy plus 2y plus k2z. Now again, we can see I'm actually getting back more of my original function. I just need to solve this. So what do? I use the third function right there. And here we can write down here, I know the partial of f with respect to z is equal to r, which is also equal to xy plus x plus y plus 3. Now take the partial of f right here with respect to z, and I get xy, that will be 0, that will be x, that will be 0, that's zy, so that'll be a y. 2y, that'll be 0 with respect to z. Then it'll be the partial with respect to z of k sub 2z equals this right here. Xy plus x plus y plus 3. And again, I equate them, so xy cancels xy, x cancels x, y cancels y. And here's where, sadly, I am just about out of room, but we are just about done. All I'm left with is the partial with respect to z of k sub 2 of z is equal to 3. Now, since I need to figure out what k sub 2 of z is, integrate with respect to z. Here, those cancel, and I get k sub 2 of z is equal to 3z plus, now, I've taken into account x and already dealt with that, y and dealt with that. Now this is z. I've accounted for all my variables, which means this is just a constant c. Now I can take this k sub 2 and stick it in right there. Now I pause for a moment and make sure you can all take all of this in, take a snapshot, pause the video, write it all down, whatever. Because now I have to erase it all to see if we actually got what I wanted. Because now I have f is equal to, there's my f, xyz plus x squared y plus xz, I erased my k right here, plus x plus zy plus 2y plus k sub 2 of z, which was 3z plus c. And now if I look over here, xyz plus x squared y plus xz, there's my yz plus my x, I reversed the order. 2y, 3z, constant c. And I found my function f. Which means when you are solving these problems, that is exactly what you're going to have to do. Given a vector field, first determine if it's conservative by way of using those equations. Then, once you have algebraically shown that it's conservative, then you want to try to find a potential function f that gives you that conservative vector field by way of solving this system of partial differential equations. Yes, it's a whole lot of work and a whole lot of algebra. Frankly, this is one of the easier functions I could come up with, and it still took like 20 minutes to write the whole thing out. So yes, it's going to be somewhat cumbersome. Ultimately, we will have other tricks to manipulate this, but you all understand how this works. You need to know how to do all of this algebra and write it out long form correctly. So make sure you understand everything that we did here. If you need me to go through more examples, I'm obviously not going to do it here because, again, they take so long. I'm not going to fill up another 20 minutes to a half an hour just doing one more problem. But if you need me to go through more problems, if that's beneficial, let me know. Email me, see me in class when I'm on campus, and I will make another video going through one or two more of these. If there's any in your textbook in particular that when you're working on them or on your homework and say, I'm really not sure how to do this, then let me know and I'll make a video running through it.